hear me? I guess it's all right. Yeah? Okay, right on the dot. It's funny, but my watch is faster by about 4 minutes. So where's the mouse? Over there?
Yeah.
Or I can use arrows here, right?
Yeah. Whatever you feel more comfortable with.
Yeah, it all depends.
Maybe I'll just use.
And then the up and down is which button? I forgot on the mouse. This is up. That's forward.
Yeah.
And if you want to go back?
If you want to go back, you have to go over here.
Okay, all right, fair enough. Yeah. Yeah, it goes up. Well, yeah, no, that's more complex than just pushing it in. Yeah.
All set. I'll introduce you and we can go ahead.
Passing is fine now.
Y'all ready?
Yeah.
All right. I believe we're ready to move on now.
Hello.
You had a preview of our next speaker from the last speaker on one of his last slides, but our next speaker is going to be Stanislaw Piorek, and he's going to speak to us about the evolution of analytical capabilities of field portable and handheld X-ray
Hello.
fluorescence analyzers.
I'll speak louder and we adjust as go.
You're on.
Yeah, switch it on. Good afternoon, ladies and gentlemen. And by the way, do you hear me in the back? Yeah. All right, thank you. I'd like, first of all, to thank organizers for giving the opportunity to talk about this very interesting and attractive subject, of course. So I'll also want to make one more remark. Out of the portraits that you've seen on the previous presentation by Andy, my name is not finished, but that doesn't mean that there's anything wrong with that. I will take you a little bit down memory line, because I think that if you want to talk about capabilities of instrumentation, you want to show the progress, and to create proper background, I have to take you down to mid-60s, where, you know, people already were thinking about using in field this method, because X-ray fluorescence was practiced in labs and in some commercial institutions. They knew that they could do that if they had a proper equipment. There was already potential. So after World War II, when isotopes were available on commercial scale, that sort of took one of the barriers from progress. X-ray spectrometry, as you know, is an inertial atomic process. It gives you information about total concentrations of the elements, and we use to generate any concentrations or results, we use X-ray spectra, and for example, in modern handheld X-ray analyzer, you have sample that is irradiated by X-rays and produces characteristic X-rays, which from detector go to a DSP processor, which generates spectrum in MCA part of it, and from that algorithm converts it to readable results, those that can be interpreted and made decisions upon. Well, this is what it is now, but it hadn't been though. So, you know, the spectrum that we want to see is of this type. This is a modern type of analyzer that we see spectrum made from. And we want to know what is in the sample and how much. And this is what we do by looking at regions of interest on the spectra in which we do integrate the counts and then use some kind of good algorithm calibration method to predict the concentrations. But in mid-60s, the only instrument that you could find of that nature was this, Texas Nuclear Corporation TN9200. That was a non-dispersive XRF. What is non-dispersive XRF? Here, if you look at this graph, you see absorption curves for elements, 3 elements in this case. Here we have nickel, next is cobalt, and then we have iron. And those curves, as Andy showed you earlier, had absorption jump, function, drastically goes up, and then absorbs elements above it. And that has been used to distinguish from spectrum that analyzer produced the irradiation of specific element. If you measured sample once through this filter and another time through that filter, the difference in 2 counts would give you anything that you could attribute to copper, which has characteristic radiation line right there. To do this, you would have to introduce those filters right here above the detector and measure it twice that way. Here is a scintillator, and here is a photomultiplier, and this was a state-of-the-art then. And, well, how well does it perform? Well, this is a spectrum, for example, of copper in copper ore. It's excited with cadmium-109 source, and the range of energy is, say, roughly from 0 to, say, 30 kilovolt. And this is how spectrum looks like. Here are, lines of copper and iron, but they are all bundled together in a huge pile. And essentially, your computing power or, data processing device of that vintage amounted to your brain, sliding rule and memory in a form of the piece of paper. Regardless of that, people are still using this. They try to simply utilize this method, and they very quickly notice that when you change the amount of iron in ore, the copper calibration curve does change its slope. So what's the solution? At that time, we don't have any computers to speak of in terms that any could use at any more time, except computers of a big mainframe in large institutions. So they built nomograms. And here's another example of nomogram. Here for copper and zinc ores, a very important application. Whenever you measure lead, you always have zinc and vice versa in ores. Well, the nomogram is so outdated word now that my spell checker was trying to correct me always to monogram. But really, it was a nomogram that people were trying to build and use. So you measure the intensity of zinc and lead in this case, and on the graph you would try to get this intersection of 2 lines and figure out the percentage of each element. In other words, this was correction for matrix effects that Andy mentioned earlier. But as far as interferences are concerned, we have 2 kinds of them in XRF. Spectral, which come from the fact that energy resolution of the detecting system is not sufficient enough. And the other thing is that sometimes lines of X-rays produced by elements are so close that even the best detector will not recognize it. The other type of effects or interferences is what we call matrix effects, and they come from the fact that elements, when they are in sample, they interact with each other, either mostly by absorbing their radiations, and sometimes they can enhance the other element's radiation. So those problems did exist, and see, at that time people were trying to correct for them in the ways that we showed before, using this non-dispersive approach and nomograms. And here, just to give you a perception of improvement, it's a spectrum or two spectra brought into the same scale in energy. One collected with scintillation and photomultiplier detecting system with promethium aluminum combination source, that's the blue one, and the same sample, not identical, the same, but the same alloy, measured now with present day detecting system, handheld analyzer. You see, for example, two molybdenum lines, they are represented here as a pile, and of course, any mathematical approach to trying to take this spectrum apart and input it to some kind of algorithm is almost impossible. So here is another example of what does it mean in terms of self-absorption. Here is a spectra of bromine in carbon matrix, and you see that this curve, the lowest one corresponds to 10% bromine, and the top one to 60. You see that the difference between them is much smaller than from, say, 0 to 10% would be. And that gives you the magnitude of problem of absorption, of self-absorption in this case, and that's also things that you need resolution to address. So now we move very quickly to present, and I'm sorry, okay, I pushed the wrong button. We, on this slide, you see Texas Nuclear, which tried to approach multi-elemental analysis by making a wheel with series of balance filters and measured sequentially the sample, whereas at that time already 740 model from Outokumpu came along. So this is like a bridge between the old and new, I would think. And then we have another remarkable development in the meantime, while XMED 880 was fighting for much market share. Texas Nuclear actually introduced first ever semiconductor detector instrument with fundamental parameters, flavor, and they both competed quite effectively with each other, but this is remarkable in a sense that there was a first time that semiconductor detector and FPs were bonded together. But, of course, in the meantime, Sleeping Lion woke up and came along and changed their game forever by making instrument into one piece, as Lee told us earlier. So then, quickly, there was progression of progress and development. X-ray tubes, miniature X-ray tubes eliminated isotopes, and of course, SDD detector finally ended up in all those instruments, and you have now plethora of them you can pick, and they pretty much have this very similar performance. So I'm not going to be, boring you with details of that. But what is remarkable is if you go through this list, we have order of magnitudes improvement on such mundane things like the reduction of mass, volume, and specifically this barrier of one piece, energy resolution as well, and you have all analytical features of high-end stationary XRF in them. All that comes with pretty much the same cost of even less of ownership. That's remarkable, and it continues to be that way. And now all these analyzers also have a capability to use GPS, Bluetooth, so you really can go with them in hand into the field, even if your civilization, or latest gas station is like hundreds of miles away. Now, if we go to analytical or capabilities of those instruments, we need to think about how we can get numbers out of it a bit. So first task is, of course, taking apart the spectrum. And here on spectrum, we have analyzed line, and we saw also Compton scatter line. And this is what most of those analyzers do use. In terms of spectrum processing, we use the concept of inverse overlap matrix very often, especially in some applications it works very effectively. although it has some drawbacks, as any method would. And what, for example, we do, here's a typical pathological, I would say, example of lead and arsenic interference if those two elements are in the sample. Red spectrum is from arsenic, K alpha, K beta line, and yellow from lead, L alpha and L beta. So if we want to analyze for both elements, we have to use L beta for lead and arsenic, L alpha, of course, K alpha. But in order to calculate net intensity of arsenic peak, we have to subtract the contribution from lead. And this is what we do here by simple method of developing this overlap coefficients by taking ratio of L alpha to L beta from pure and using that on unknown sample to subtract lead contribution from total to arrive to net arsenic. And this is the basis of the so-called inverse matrix approach. We have this assumption of linear combination that we, in each region of interest, we consider the overall count to be a sum of all contributors. But since we are interested in net intensities that come there, we need to simply inverse this equation. And that is happening in a matrix type domain. Here for 3 elements you have forward, and here you have inverse matrix. You see that coefficients on diagonal are close to 1 as they should be, and on rows and columns which are heterogeneous there, you have contributions from the neighboring elements. In practice, you can see something like that in instrument, and of course you cannot see it well, but for example here there is contribution of zirconium to molybdenum, and this is what we use quite often because it's fast. And when we address its limitation, then we can also use it in broader applications. This deficiency of coming from the assumption of constancy of the ratios of lines can be taken care in algorithm, in FP, different ways, but this is a detail that I don't think we need to discuss right now. Here is an example of what happens when you take an alloy and measure its gross intensities, represented here with blue lines, and with red you have net, and then after this subtraction goes on, and then you have the results on the bottom. So it works with limitations as always, but it does. As far as quantification routines, typically we have either empirical or fundamental parameter-based flavor of methods. And in terms of empirical, the most popular have been Compton normalization and mentioned earlier intensity correction model by Lucas Student Price. And in terms of fundamental parameters, modifications of different alpha coefficients models. So briefly, Compton normalization simply uses the fact that absorption of scattered radiation undergoes similar process as absorption of element of interest line in the sample. So by taking the ratio, we sort of linearize the problem and make a straight line calibration effective. Sometimes you can add second order to it to get better fit. Now, it has also limitations that it mostly works in the cases that I outlined here, and it also breaks down when you have absorption edge of one element between Compton radiation and the element of interest in sample. So next method used when you do not have yet FP available, Lucas Student Price correction method, intensity correction method. The beauty of it is that concentration of element is related only to intensities of all the elements in sample. And what it means is that you'd only need, for standards, you only need to analyze for the element of interest. In other words, you have to create assays for only the element of interest, and you don't need to analyze for all the others. But nevertheless, all those methods require a lot of standards to calibrate the instrument. So finally, when computers were so popular and had so much power, and they could be miniaturized to the point of something like palm device, we could put fundamental parameters algorithm, which are really mathematically and calculational extensive algorithms in a handheld instrument. Here what I show you is simply already much simplified equation of fundamental parameter flavor. Here concentration of the analyte is related to relative intensity of that analyte relative to pure element intensity. And then you have a host of different coefficients which are also functions of the concentrations of the elements and the analyte itself. So the problem here is that we have variable that we are looking for, or unknown, on both sides of the equation and in not very straightforward manner. Therefore, you have to solve this kind of thing numerically using iterative procedures. And of course, if you have more than one element, you need to do this for all of them. So eventually, you are ending up with solving a rather large matrix equation system in iterative way. Now, but it has this very strong attributes that it does not necessarily need so many standards, if at all, and sometimes totally standardized approach is also feasible. The fact that we can write full, complete equation that is based in physics, that describes interaction of X-rays with matter, is probably one of the unique features of this method of X-ray fluorescence. It's not necessarily true to say that about all the other methods that we use in the lab or not. So this is very unique, and it's now possible to make use of it, even if it was invented already and formalized in mid-50s. Just for the sake of completeness, what are fundamental parameters? There is a bunch of these physical constants derived by scientists and measured, and that's why it is called fundamental parameters-based approach. Sometimes people are asking me simply what fundamental parameters are, so that's why. We're going to applications. What all this progress in instruments and technology of making them, combined with software that has been developed for it, all this made possible some applications. The whole plethora of them you can count, but if you look at it globally, you will see that most of it is analysis and IDing of alloys, metal alloys. Next probably comes a market which we call environmental in global sense. It's screening of soils, testing consumer goods and toys, and for example, making sure that products are compliant with RoHS directives. That would be minerals, and then all the others. And when we look at alloys, Andy told us something about steels. Now here are high temperature alloys and steels, and then we have stainless steels. Here you have steel type or grade, and here's its composition on this line. So you see that if you look by elements here, you have quite a different concentrations that they can be distinguishing factor when you look for identification of these alloys. So it's not necessarily impossible. Actually, it is very good medium to analyze by XRF because it's almost like solidified solution, a homogeneous solution of water solution. So that's one of the reasons that it's so successful. On the other hand, there is a need for it because if let's say you take a stainless steel grade in which you know that you have to have between 10 and 12% of chromium, and say matrix of iron should be between 95 and 100% plus some other alloying elements, you would hope that that chromium or any other element would be in the middle of its specification range. Well, that's not so, because chromium will be always biased to lower, and less expensive elements such as iron would be biased to the higher limit. So you need to check that specifications are still maintained, and that's the main reason behind analyzing steels and alloys. Now, here you can see that in air, you can measure, for example, the difference between 304 and 303 stainless steel, and the difference comes only from the sulfur content. And of course, the other problem here is that you have to really clean the surface of the alloy if you want to measure elements such like elements as sulfur or say phosphorus. But it is possible to do it in real time in less than 10 seconds and in air. Next, the specific application in the arena of alloys is, for example, zirconium in zircalloy 2 and 4. These are two alloys which are used in reactors, and the difference of nickel makes, nickel content makes a whole difference in terms of corrosion resistance. We have to look at several hundred ppm of nickel there. So when you look at spectrum, this nickel peak here is quite tiny, yet you still can measure it and distinguish those two alloys before you put them into reactor. The other big application that I mentioned to you, family of them in environmental, is soil screening. And as it was mentioned earlier, the efficiency of this is tremendous in terms of time and cost. Here's, let's say, hypothetical contamination site with plum of contamination here. And now, classically, what we would do, we would came and with analyzer maybe, or with a lab technician would come in and took some samples here, all right, randomly spread, because we don't know where actually plum may be. Usually contaminated sites do not have much history recorded for obvious reasons. They may be very old, or simply people who did that damage didn't really want everybody to know about it. So now with screening, using handheld or portable X-ray, we can actually go and measure every meter, in steps like that. We can cover that in few hours, all right, and then you will delineate the problem. Now, the fact may be that our analysis may not be super accurate or precise, that's given, but you have the profile, that you have simply localization of the problem, and then you can pick and choose some samples to send to the laboratory for a more accurate analysis, and then you can actually scale all your profile to give it more accurate values altogether. Tremendous amount of saving in cost, time specifically, and not only that, but this kind of analysis can also be used dynamically on the site when remediation takes place. You can go in, and after they remove some layer of soil, you can check right there whether the removal is successful. As far as detection limits, these are typical in pure silica and in certified reference material. As you can see, as Andy mentioned to you, these are real. That's what you get in field, and these are pristine. That is, calculated in a lab conditions and measured in a pristine matrix. We always have this issue with detection limits, which simply are sometimes overshadowing the real problem that there is out there. EPA method 6200 covers this thing acknowledges this as a field portable instrument for screening soil. ISO is developing also standard for that same purpose. This means that it's recognized throughout. Now, in 2006, we got RoHS and WE directives introduced that banned some elements in electronic products. And here again, X-ray is used as a first step for screening, and if you find that the product is compliant, you don't have to go through extensive testing. If it is not, then you can reject it. And when it's inconclusive due to errors of measurement and so forth, you still can go forward with it. Here it shows you that very small items can be measured when you collimate the beam properly with very good accuracy even. And so then you can even go and pick up some solder joints that are not compliant. Here for polymers, detection limits for polymers, again, similar like for soil. What I would say is significant here, you have chlorine. Chlorine is measured now also as one of the fluorocarbons that they banned from use, and chlorine belongs to them. That's why we show chlorine measured here as well. We have also Consumer Product Safety Improvement Act of 2008, which was an aftermath of the fiasco with lead in toys discovered in 2007. And right now, lead is limited to 100 milligram in any material but paint. In paint, it cannot be more than 90 ppm. And CPSC is actually using a bunch of these analyzers for screening. And also European regulations address the same problem, although slightly different way. But here, you know, you can have lead in all kind of issues associated with not only with toys, but with consumer products as such. And for example, you know, this collimated beam can measure very effectively lead presence in this duck's eye, while if you would scrape that paint, you may not necessarily get that analysis done in a lab. All those dinos were also showing a lot of lead in their paints, and perhaps that's why they got extinct. You have to be careful also when you follow some, you know, things published in papers or in media. For example, you probably heard about lipstick scare. There was a big uproar, because there is some about 1 ppm lead in lipstick in some of them. Okay, so what does it really mean? You know, the same report which talked about it, they said that, you know, average female is consuming about 4 pounds of lipstick in a year, in a lifetime. I'm not going to get into age, okay? But let's assume 50 for sake of argument. That means, I'm sorry about it, that means that it's total of about 3.6 milligram of lead total, okay? So I'm not going to try to trivialize the issue, but if you have handheld analyzer, you can quickly check that you can still kiss the bride and be safe. Mining is a new area for this to go and help, especially now when we have to mine for less and less efficient ore bodies. I here want to show you only, here's a piece of rhyolite rock with nice stripes of you know, red and white. And when you go and scan it with some handheld X-ray, you see that these peaks correspond to red, and they are iron. So it shows you also capability of all kind of using this in field, not necessarily in a lab environment. In art, people use very often handheld analyzers to see, for example, whether the paint they need to use to repair object or conserve it will have a proper composition so it matches original. In conclusions, I will summarize it, and I would like to piggyback on whatever summary we heard so far, because they are simply complementing each other. It's very difficult to list them all. But I believe that because of inherent features of XRF, meaning non-destructiveness, multi-elemental, and simultaneously multi-elemental, it makes it, together with technological development, the one to go with into field and do measurements on-site at the point of use. It is accepted as a method of choice in many areas, and it will be developing in this direction. What to expect in future, and that's my last one. Incremental improvements here and there. There will be higher voltage tubes, or perhaps maybe more desirable higher current tubes. What we need to really concentrate is the development of robust algorithms, because we need to make them more universal. The amount of samples and type of them that people want to test is very, very diversified. And usually when you talk about samples such as consumer products or any kind of products, they are by nature heterogeneous. They are not pristine. They are not nice medium to analyze. You have to then have some kind of means to account for that to be helpful. Okay, and on that note, I'd like to thank you for the attention.
We're a little short again, but we might have time for one question. Does somebody have a question? If not, then we'll move on to the next speaker. Alan?